Okay, in this example, we have a bridge that weighs 5,000 newtons and is 40 meters long. There's a car on the bridge, and its center of gravity is located 12 meters from the right pier. So there are upward forces, FL and FR, on the left and right sides of the bridge. So let's go ahead and draw these in. I'm starting mine with this shape here to represent the bridge. And we know that the bridge itself has weight. We're going to draw that here. That's the weight of the bridge. There's a car here. Let's see. It's 40 meters long, so this is 20 meters from here to the center. And the car is 12 meters away. So that's more than half of this, so maybe about right here. Weight of the car, that's 1,500 newtons. Weight of the bridge, 5,000 newtons. Now, just as important as putting the forces is where you put them and labeling where you put them. So 12 meters right here. And then we've got the support forces. So the bridge is sitting on things, and they call one of those things a pier. Okay, that just means it's sitting on something. So something's pushing up on it. So we've got FR and FL. So we have two unknowns. And so if we said, hey, that's the positive y direction, and not that we need it, but that's the positive x direction, then we would sum the forces in the y direction, set it equal to MAY. We could say FL plus FR minus 5,000 newtons minus 1,500 newtons equals the mass of the bridge, which we could figure out, but we don't need to because we know the acceleration of the bridge is 0. And then we have two unknowns. So if we have two unknowns, we can't solve it. But that's why we have the torque equation. So we can go ahead and sum the torques. That's the Greek letter tau, equal to I alpha, where alpha is the angular acceleration. And because it's an equilibrium problem, alpha is 0. Now to sum the torques, we need to have a positive direction for torque. So as always, I'm going to pick counterclockwise to be my positive direction for torque. So if, let's just say the right end of the bridge is my axis of rotation. Go ahead and label that. Put a little circle there. That's my axis of rotation. So then FL times, well, I didn't label how far that is away. That's 40 meters, the entire length. So FL is acting 40 meters away. So FL times 40 meters times the sine of 90 degrees. But remember, sine 90 degrees is 1. And all of these forces are acting at right angles compared to the distance. So FL times 40 meters times the sine of 90, and that's acting in the negative direction. Okay, if you don't believe me, you can lay your pencil on the screen, hold it at the right end, and then push up at the left end, and you'll see it rotating clockwise. And that's the negative direction. All right, what else? Well, then we've got the weight of the bridge, which is, well, I'm not going to write it as that. I'm going to write it as 5,000 newtons times 20 meters. And that's acting in the positive direction. The 1,500 newtons from the car, that's 12 meters away. That's also acting in the positive direction. And then plus FR, that's 0 meters away. So it's not creating any torque whatsoever. And we say that's equal to 0. So FR times 0, that means that's not in the equation anymore. So we picked this location to be our axis of rotation, but it would have worked just as well if we had picked the left end to be our axis of rotation. We could have also picked the center to be our axis of rotation, but then we would have ended up with two equations and two unknowns, and we could have solved it. It just would have taken more time. All right, so minus FL times 40 meters, and then we do the math on these parts right here, and let's go ahead and do that right now. And that gives us a value of 118,000 Newton meters. And then we solve for FL, and we get 2,950 newtons. We can then take that value, and that is one of our answers. We can take that value and we can substitute it in right there. So then we can solve for FR, and we get a value of 3,550 newtons. And I'll let you do the intermediate algebra steps in each of these equations, but I think you'll agree with me. And it makes sense in this case that the right support is going to be exerting more force, supporting more of the load than the left support over here. And that's because this car is parked over here to the right of center, and so that's putting more force, causing more force to be needed over here. And as I said earlier, we could have picked anywhere else to be our axis of rotation, and I encourage you, go ahead and get a new piece of paper and make the left end of the bridge your axis of rotation, and go ahead and solve it that way, and you should get the exact same answers. Go ahead and try it.